So let's go back to that example where we were talking about the frequency distribution that we created from the baby birth weights. Let's briefly talk about the patterns we saw there. So we have 4 classes. So each of those birth weights is categorized as between 5 and 6, not including 6, between 6 pounds and 7 pounds, not including 7 pounds, and so on. Notice that the largest amount of baby birth weights are between 7 and 7.9 pounds. Okay, so that's more frequent in this sample. And next were the 6.0 to 6.9 group and the 8.0 to 8.9 group, and then just one single baby born in the 5.0 to 5.9 pound group. But there are other ways to express or to organize this information. Frequency is helpful. You can tell the differences between those counts, those frequencies pretty well. But sometimes it is not all that useful to represent the raw data like this. Sometimes we're interested in expressing it in terms of percentages or proportions, just like we did with categorical frequency distributions. So what we can do now is we can create relative frequency distributions, which, for the sake of clarity, a relative frequency distribution is the class along with the relative frequencies table. Okay, you don't need the frequencies there. You can if you want to, but we don't need them. What we also need, though, is we need the sample size. And remember, we said that was 48. So what we'll do then, every relative frequency is computed as the frequency divided by the total number of data points, the sample size. So the first one is 1 divided by 48, 1 over 48. And you can express them as fractions if you want, but oftentimes we represent them as decimal numbers, which is easier on the eyes. And we're going to always approximate to no more than 4 places after the decimal. So 1 divided by 48 is approximately 0.0208. So there should be an approximately sign here. 11 out of 48 is 0.2292, roughly, if we round. And then 29 divided by 48 is roughly 0.6042. Lastly, 7 divided by 48 is roughly 0.1458. And so, these are relative frequencies expressed as decimal numbers with 4 places after the decimal. You can roughly think of this as these are precise to the 10,000ths. And how you know you've done this correctly is if you add up all these relative frequencies, and if you've rounded, you might be off by just a tiny amount, but I'm currently calculating on my handheld calculator. If you have your TI-84, that's a great tool, or even a phone calculator will work, to be honest. And so when I've added up all these relative frequencies, in their decimal form, I actually get 1. So they add up to 1. And that is an important attribute of relative frequency distributions, that when you add up all the relative frequency distributions, you should get 1. Okay, and that's how you know you've done it correctly. There's a similar tool that we can use that's a little different, and it's not something that can be applied with categorical data. This only works with quantitative data because there's no natural order that we use normally with categorical data. So it's rare. You can use it sometimes, but for the most part, we'll be using it only with quantitative data. And the way cumulative frequency works is instead of calculating, proportions or the frequencies themselves, what we can do is start with the very first class, and the first cumulative frequency will just be the first frequency. The next cumulative frequency, so for the 6.0 class, we'll take what we had in the previous cumulative frequency and add on the next frequency. So if you are a visual person, you want to see the pattern, I'm taking the 1 here and the 11 here and adding them together to make my new cumulative frequency. You can think of cumulative frequency as how much have we accumulated so far, right? So mu means to collect, right? So we're collecting all those data points. What we're essentially saying is in each class now, we can interpret it as less than 5.9 or less than or equal to 5.9. Or I guess, we can put less than. So less than 6.0 is the first one. And now the second one, we can kind of think of it as less than 7.0. So we're just taking all the babies' birth weights who are weighed less than 7.0 pounds. And so that's 12. And we keep going down the line. So the next one will be 12 plus 29. 12 plus 29. Which should be 41, if I'm not mistaken. So the last one will be 41 plus 7, which is 48. And just like we modified the other classes, then that means then the last two classes we can think of as representing the less than 8.0 and the less than 9.0. And since all of the data values were less than 9.0, it makes sense that the very last cumulative frequency is the sample size. So here are the patterns numerically, if you like to think about formulas. Each kth cumulative frequency, so the kth cumulative frequency is the sum of all the ones before, the sum of all the frequencies up to that class. So starting with the first class and up to the kth class. So if we're looking at the third one, right, you add up frequency 1, 2, and 3. That's what this notation means, okay? It's the summation notation. As a reminder, summation notation is covered in the appendix. So if you're really confused about this, go ahead and take a look at that. But otherwise, this isn't an exactly necessary formula. It's just a way for us to represent it numerically. And you've done this correctly if the last cumulative frequency, which I'm going to denote CF, is the sample size, because that is the sum of all the frequencies, which should be the sample size. Okay, so those two things undergird what we think of as the cumulative frequency distribution. So really all you need for these kinds of tables are, again, the classes and the actual cumulative frequencies, which are 1, 12, 41, and 48. And you'll notice that they're increasing in value, okay? Because each time you're adding a few more data values, hence cumulative.